Alright, so now let's use our knowledge of combustions and mixtures and molecular weight to analyze a system like this. It's a combined cycle. There is a gas turbine cycle over here, compressor, combustion chamber, gas turbine, and the exhaust is too hot. So the cycle is running 1 to 2, 2 to 3 in the combustion chamber, 3 to 4, and then 4 is too hot. You know, he doesn't want to throw it away. So what do? We send the 4 into a steam power plant, a Rankine cycle, and you can see he has 2 feed water heater over here, one closed and one open. That steam power plant has a boiler. That boiler take the steam and take the liquid at 780 and 1200 psi and turn it into steam at same pressure but at 1560 Rankine. So that boiler to turn the liquid into vapor need heat, and so he fired this with the exhaust from 5. Sorry, the exhaust from 4. The exhaust from 4. But because 4 is high but not high enough to do the job, he have external boiler, or like a supplementary firing device, so or auxiliary firing. So he's basically send a little bit more fuel to take you from 4 to 5. Now 5 is hot enough, he send it at constant pressure into that boiler and it go all the way to 6. Now at 6, after turning all that fuel, turning all that water to steam, now 6 is cold enough that it's okay to throw it away. Okay, so by combining the gas turbine to the steam power plant, you benefit from basically that 4. You don't want to throw it away, you benefit from this hot gases. So it look complicated, but he's actually asking for very simple thing. He's asking how much Q he need to send over here. The Q that we are sending in BTU per pound of air, the air that we are sending here. That part is complicated, per pound air, because what's coming in here now is not just air, it's air with fuel. Okay, so I mean, if you neglect the fuel part, the problem become much easier. But if we want to do a good job, and we will do a good job, then we have to count, basically turn from the exhaust mass flow rate to just pure air, because that is the deal. He wanted the calculation per BTU per pound of air. Okay, so how much air he's sucking through the compressor, you need to figure out how much fuel he need to send in here. And the second thing that he would asking about is the m dot air per m dot steam. So that m dot air that the gas turbine is sending, if you are saying 10 kilogram per second, how much kilogram per second of steam you are gonna generate in the steam power plant. Okay, so how we can solve this? I mean, let's solve the easy part first, the m dot air over m dot steam. If I want to figure out how much m dot steam is flowing in the cycle compared to how much m dot air is going through this, what should I do? Conservation of, no, not conservation of mass, because that basically tell you m dot water is equal to m dot steam, and it will tell you whatever m dot is going through here is going to be the m dot over here. So they are not tied together with the mass, they are tied together with energy, right? So the energy this guy lose is going to be equal to the energy this guy will gain. So m dot steam time this delta H, he come at 780 and he leave at 1560 at the same pressure, because it's heating at constant pressure. Remember the Rankine cycle? The Rankine cycle is, you basically send him the water like this and it go all the way to this. Alright, so if he's gonna 780 over here, right, he's gonna go all the way to 560, right, degree Rankine, and all this is happening at what pressure did he use? The 12, what is it? 12,000 psi, right? All this is happening at 12,000 psi absolute. This is the TS diagram. So if I get this H and I get it from the steam table and I get this H, then obviously that boiler is using m dot steam is gaining m dot steam multiplied by that delta H steam, right? This is the Q that is added in the boiler. This same Q is the same as what the exhaust gas is losing when he's going over here. So it's gonna be m dot product, actually not m dot air. It's the point is it's gonna be the Q that he's losing. So all we need is this H6 and H5, and I'll be able to get the mass ratio between this and whatever is flowing over here. Okay, so we need those H's. We need H5 and H6. Okay, so then we'll be able to solve this. Now for the first part, the Q supplementary firing, he need to figure out how much he need to add over here, how much energy need to be doing it. Well, I will do what to get this Q? First law again of thermodynamics, right? This course is, most of the time you are just basically applying the first law of thermodynamics in most problems. So in order to get this Q, that Q will be m dot multiplied by delta H, H5 minus H4, 5 minus 4. So we just need H5 and H4 and we'll be in good shape then. So let's see what is given to us. We are given those temperature and pressure. We are also given T3, we are given T5, and we are given T6. 5 and 6, perfect. Right? And we are giving the pressure ratio, it's 8. Remember, the gas turbine cycle efficiency depends on the pressure ratio. And we are given the turbine isentropic efficiency. So it's not isentropic, he have 0.9. Okay. So, and we are given H3 too, right? That's nice. So, how are we gonna get those H's? H5. CBT, right? Yes. If you assume CP and you know the temperature, you can get away with this in the exam, CBT. But to make it more accurate and more complicated in this example, he is actually using tables for air. There are tables. So ideal gas, yes, CBT, perfect. But there are tables that account for the variation of CB with temperature. Not just the variation of CB with temperature, but the variation of CB with composition. See, is firing here fuel CH2 1.45. And yes, the fuel to air ratio is very small. This is mainly air going through. We can neglect the fuel and assume this is just pure air. But for accuracy, you should account for the fuel changing the composition. Okay? So this is pure air, and he's saying this is the air that he's using here is 400% the theoretical air that's needed to burn that fuel. And already the 100% air that is required to burn this fuel is already a lot of air, right? So 400%, that ratio, that means that this is just way too much air. So this is really can be assumed all air. And why they are using so much air in gas turbines? Because they are worried about the turbine. They don't want to burn the turbine. So if they let it to stoichiometric combustion, remember the Excel file of Dr. Daly and how high the temperature gets? That will melt the temperature. That will melt the plates of the turbine. So that's why they use a lot of air to lower the temperature. Remember, when you burn fuel lean, the temperature drop. Yes? So what I'm saying is that if you're gonna get H5 and H6 just based on their temperature and multiplying this by a CB of air, that is fine in the final exam, definitely, right? But in this example, he's gonna use tables to calculate the CP based on that temperature and based on, is it air or is it air with product? Okay, and when it's air with product, he can tell the right CP for using this. Okay, so that's just more accuracy. And so the air here is 400% what's required. So meaning that this is CP air, but over here that is air with product. and how much product? 400% air ratio. So that tell him how to use the table with the right amount of product in the exhaust. And once he leave, he get fired, and he said he will fire with enough fuel to make it 200% theoretical air. So again, he will open the table over here, saying that I got at 5, I got 2000, and I had 200% theoretical air, and that would allow him to get an accurate H rather than just using the Planck CP 1004.5 multiplied by the temperature. Okay, so bear with me in this example where he's basically using table. Again, in the final, you can go ahead and just assume CPT. So he's saying use table for 400% theoretical air, and so in those tables, just like the steam, you need two properties to get the H. Okay, so you need the pressure and temperature, you get H3. Okay, so I guess it was not given. He calculated it. And now, how do we get 4s and 4? This is isentropic, right? And then you will be able to 4s, you will be able to calculate H4s. Okay, and how do you get 4s? Isentropic. So T over T is P over P to power gamma minus 1 over gamma. And once you get T, you get H from it, right? So all you need is the temperature and the pressure, you get the H, and you're using the table for 400 theoretical air. And then the isentropic efficiency of the turbine will take you from actual work to theoretical work. Actual work, which is H3 minus H4, to theoretical work, which is H3 minus H4s. So you got the theoretical work using the eta of the isentropic efficiency of the turbine. You will be able to calculate H3 minus H4, which will allow you to calculate H4. Right? H4 is bigger than H4s, obviously. It's over here, and you got yourself H4. Now we have H4 and H5, and we can say that the Q supplementary fire is H5 and H4 multiplied by m dot, and since he wanted it per unit mass, so the Q per unit mass is simply H5 minus H4. Perfect. We are done with the first part, except that when we did this H5 minus H4, it's all BTU per unit exhaust, unit mass exhaust. And what's even more complicated in this scenario or in this example is that that table gave it to him per pound mole, or basically kilomole of gas, not kilogram. So two problems. First, it's per unit molecular weight, unit per kilomole, and the second thing is that it's per kilomole of gas, not per kilomole of air. Okay, and the results wanted the Q to be per unit mass of air. So we need to convert between the mass of the exhaust and the mass of the air. What is that ratio? If I have 1 kilogram of product, how much kilogram of air do I have? The fuel to air ratio. That is a trick, right? So if I have fuel plus air, I will make product. So the mass of this thing is the mass of the fuel and air. So the ratio between product to air, the mass ratio of product to air, is fuel to air over air, or basically it's 1 plus fuel to air ratio. Okay, this is how you turn from kilogram or pound mass product to kilogram of air. You need the fuel to air ratio. So how he's gonna get the fuel to air ratio? He's looking at CH2.145. That is fuel, and we did this in the look to the previous lecture. You will know how we can get the fuel to air ratio of this guy. So you tell yourself, I got this CH2.145 plus O2 plus 3.76 N2 what is the fuel to air ratio stoichiometric, and then later we do the 400% because he said it's 400%, right? So what do we do? Previous lecture, you do CO2 and you do H2.0 for complete combustion. How much H2O? This guy 2.145 divided by 2, conservation of mass of the hydrogen atom, and then you bag those number over here, right? How much O2 we need? M plus N over 4, right? M is the number of carbons, so that's 1, and N, that is this number, the 2.145 divided by 4. Why by 4? Because you get 2 over here, and then this is O and this is O2. So this will tell you how much. So let me do this. So this will tell us that to burn this weird fuel H2.145, you need 1 plus 2.145 over 4 O2 plus 3.76 N2. That will give you complete combustion, right? And now if we want the fuel to air ratio or the air to fuel ratio, and then we will invert it, you'll just have to calculate the mass of the air divided by the mass of the fuel, right? What is the mass of the fuel? 12 plus the 2.145 multiplied by hydrogen is 1, and the mass of the air is this big number over here, 2.145 over 4 multiplied by this is the number of moles, right? Multiplied by 32 plus the 3.76 multiplied by 28, right? So that will give you the air to fuel ratio. That's the theoretical, right? That's the theoretical fuel to air ratio. So that's basically what he did over here. So what we did right now is we'll give you 14.91. So the product to air mass ratio is 1 plus 1 over air to fuel ratio. It's become 1.033 for 200%. So this is stoichiometric. You need to make this twice as much for 200%, and it's 1.168 for 400%. And you can also calculate the molecular weight for both scenarios. Molecular weight of what? Of the product. Why do we need that? I'll show you in a minute. So we said we have two problems in our H's that we are calculating in this example. One problem is it's per unit mass of gas, and that's why we wanted to know what is the conversion between the mass of the product and the mass of the air. That's the first problem. Second problem is it's per pound mole. So BTU per pound mole, not BTU per pound, BTU per pound mole, or basically saying it's BTU per kilo mole, not per kilogram. So I want to turn it between kilomole to kilogram. What is conversion? Molecular weight. What's the units of the molecular weight? Kilogram per kilomole, kilogram per kilomole. How did he calculate this? Those guys, right? So CO2 plus 2.4 H2O plus the nitrogen that will come out. So 1 plus 2.145 over 2 multiply by 3.76 into. So this plus this plus this, those are the moles of the exhaust, right? And if you want the molecular, if you want the mole fraction, you divide each one of them divided by the total, right? And if you want to get the molecular weight of the mixture, we did this last time. M mixture is sigma yi mi, where this was the molecular weight of N2, the molecular weight of H2O, the molecular weight of CO2 multiplied by the mole fraction of each one of them. Okay, you'll be able to get the mixture. molecular weight. This is for stoichiometric. For 200% air, you multiply the number that you will come. This number will be multiplied by 2, and for 400%, this will multiply by 4, because you have 4 times the air that is being generated, and then you will end up generating O2, right? If you have 200% extra air and 400% extra air, you generate O2 in the product. Alright, so he get the mass fraction, or sorry, the mass conversion between product and air, and he get the molecular weight. So what he will do is this: he will be able to convert H5 and H6. H5 and H6 and H4, he will be able to convert those number to here H4 and H5, H6. All this was done so that he can convert to BTU per pound mass air, right? So first he multiplied by the product to air ratio to turn it to, actually let's do it this way first. First, let's divide over the molecular weight so that it become BTU per pound mass of product, right? Each one of them is divided by the molecular weight, 28.925 or 28.880, depending on, are you 400% or 200%? Before the supplementary firing, you are 400%. After the supplementary firing, you are 200%. So the mixture molecular weight is different between 4, 5, and 6, right? So we divide the H by the molecular weight. Now it's BTU per pound mass product, and then you multiply by the product to air ratio, right? So then now it's BTU per pound air. Of course, in the final, to make your life easier, maybe I will just give you the H, since you don't have access to those tables. So I'll just either give you the BTU per pound mass air or joule per kilogram air, right, directly, okay, or I will just tell you just use CBT, and here is the CP. So every one of them you just say CB multiply the temperature, that is the H. But that doesn't save you from what? From this part, that this is mixture, and if he want, this is fuel and air exhaust, and if you want it per unit mass, you still need to use the fuel to air ratio, right? Okay, so now he got all his H's: BTU per pound air, BTU per pound air, BTU per pound air. So the supplementary firing, how much Q per pound air? First law of thermodynamics. So there was, if this was, this is per unit mass, right? But if I wanted it, the original one was basically like this: m dot air, right, multiply by this. The Q dot was m dot time H. That's the first law applied to this place. So the fact that you don't see m dot air over here, ouch, the fact that you don't see m dot over here is because he is doing it per pound mass. Okay, so first requirement, we got it. So long route, but the equation is very simple. If you want to know how much Q is coming over here, it's m dot delta H, m dot delta H. And so if you wanted it per m dot, you basically say Q per m dot, or is the Q per pound mass, is simply delta H. Done. Perfect. What's the second thing he wanted? The ratio between m dot air and m dot steam. So what do we do? First law of thermodynamics. So the bottom line is this, The bottom line is this equation: m dot air multiply by what? H5 minus H6, right? M dot air multiply by H5 minus, it should be H6 minus H5. No, 5 minus 6, because 5 is bigger than 6. M dot air H5 minus H6 equal to m dot steam multiply by delta H steam. What's delta H steam? That H minus this H. You open the steam table and find out what is the H over here, 1500, and what is the H over here, 290, the difference between them is this much per pound steam. This is your delta H steam, and H5 and H6 we have them, right? So you basically say, well, m dot air over m dot steam is simply this divided by this. Alright? Good job.